Okay, hello everyone. Let us continue the third part of today's class. Okay, in the second part of today's class, we have taught to here. Okay, the true gradient of Q of W is approximated by a gradient at a single sample. Okay. Okay, so we calculate W minus eta, okay, where eta is the learning rate, and times the gradient of Qi of W, and then assign it to W, okay, to update the value of W. Okay, compare this equation to equation 23. Okay, you can see that the 1 over n and the summation I is equal to 1 to n, okay, disappear. Okay, let us go back to here. Okay, as the algorithm sweeps through the training set, it performs the above update for each training sample. Several passes can be made over the training set until the algorithm converges. If this is done, the data can be shuffled. Okay, what is shuffled? Okay, let us see what is shuffled. Okay. Okay, problem 45. What is shuffle? Okay, solution. To move similar things from one position or place to another. Often to give an appearance of activity when nothing useful is being done. Okay, this means the shuffle. Okay, let us go back to the first shuffle. Okay, so be shuffled for each pass to prevent cycles. Okay, or prevent the loops. Okay, you know when you write a computer program, you sometimes you will write a loop. Okay, for example, for loop. Okay, if you do not write your computer program correctly, then you will produce an infinite loop. Okay, typical implementations may use an additive learning rate so that the algorithm converges. Okay, what is an additive learning rate? Okay. This means that the learning rate can be changed in every iterations. Okay, it is not a constant. Okay, in pseudocode, stochastic gradient excuse me. Descent can be presented as. Okay, first choose an initial vector of parameters w and learning rate eta. Okay. Second, repeat until an approximate minima is obtained. Okay, you should note that the learning rate, value of the learning rate is always greater than 0 and smaller than 1. Okay, and in the most cases, we usually choose a very small number as the learning rate. Okay, for example, 0.01 or 0.005, etc. Okay, third, randomly shuffle samples in the training set. Okay. Fourth, for I is equal to 1 2 to n, do the following. Okay, we compute w minus eta times the gradient of qi of w and assign this value to update the value of w. Okay, a compromise between computing the true gradient and the gradient at a single sample is to compute the gradient against more than one training sample, called a mini batch. Okay, we have in the second part of today's class, we have said we will introduce what is a mini batch. Okay, here. Okay, at each step, this can perform significantly better than true stochastic gradient descent described. Okay, because the code can make use of vectorization. Okay, we will introduce what is vectorization later. Okay, libraries, rather than computing each step separately as was first shown in reference 107. Okay, let us see this reference. Okay, reference 107 is written by J. Bilmes, K. Asanovic, and C-W. Chin and J. DeMille. Okay, using PHYPEG to speed error backpropagation learning. Okay, backpropagation is also an important concept or algorithm in the deep learning. Okay, in 1997, IEEE International Conference on Acoustics, Speech, and Signal Processing. Okay, so this is a conference paper. Okay, now let us go back to the location which we cite a reference 107. Okay, where it was called the bunch mode backpropagation algorithm. Okay, what is the meaning of bunch? Okay, let us see. Okay, problem 46. What is bunch? Okay, solution. A number of things of the same type fastened together or in a close group. Okay, this is the meaning of bunch. Excuse me. Okay, let us go back to the first bunch. Okay, here. Okay, it may also result in smoother convergence as the gradient computed at each step is averaged over more training sample. Okay, so this is the concept of the mini batch. Okay, the convergence of stochastic gradient descent has been analyzed using the series of convex minimization and of stochastic approximation. Okay, convex minimization and stochastic approximation are two series. Okay, and due to the time limitation, I do not intend to introduce them here. Okay, briefly, when the learning rates eta decrease with an appropriate rate and subject to relatively mild assumptions, stochastic gradient descent converges almost surely. Okay, I will introduce what is almost surely later. To a global minima when the objective function is convex or pseudo-convex. Okay, I will introduce what is pseudo-convex later. Excuse me. Okay, and otherwise converges almost surely to a local minima. This is in fact a consequence of the Robbins-Siegmund theory. Okay, I will introduce what is Robbins-Siegmund theory later. Okay, let us see an example. Okay, let us suppose we want to fit a straight line. A y hat is equal to w1 plus w2x. Okay, so here w1 and w2 are two parameters. To a training set with observations x1, x2 to xn and the corresponding estimated responses y1 hat, y2 hat to yn hat using least squares. Okay, I will introduce what is least squares later. Okay, the objective function to be minimized is q of w is equal to summation I is equal to 1 to n and qi of w. Okay, so excuse me. So it is equal to summation I is equal to 1 to n yi hat minus yi square. Okay, then we substitute yi hat by y hat. Okay, and y hat is replaced by yi hat and x is replaced by xy. Okay, then this equation is equal to summation I is equal to 1 to n w1 plus w2xi minus yi squared. Okay. Okay, the last line in the above pseudocode for this specific problem will become. Okay, let us go back to the above pseudocode and see the last line again. Okay, here is the pseudocode, and the last line is to compute w minus eta times the gradient of qi of w and update the value of w. Okay, let us go back to here. Okay, so w1, w2, this vector is updated by this. Okay, the vector w1, w2 minus eta, the gradient, okay, of the q function, okay, of the qi of w. Okay, so this should be okay, a partial over partial w1. Okay, w1 plus w2 times xi minus yi squared, and the second element is partial over partial w2, w1 plus w2 xi minus yi squared. Okay, so for the first element, let us take the partial derivative of this term with respect to w1. Okay, then according to the chain rule, this is the form of x squared. Okay, so we find the derivative of x squared is equal to 2x. Okay, and according to the chain rule, we need to find the derivative of this term. Okay, with respect to w1. Okay, so according to the technique of partial derivative, w2xi and yi are treated as constants. So finally, it is the partial derivative of w1 with respect to w1, which is equal to 1. Okay. So next, we need to find the second element. Okay, here. So again, we need to find this term, the partial derivative of this term with respect to w2. So first we use the chain rule again. Okay, this is the form of x squared. So the derivative of x squared is equal to 2 times x. Okay, so next, according to the chain rule, this term should be times by the partial derivative with respect of this term with respect to w2. Okay, so when taking the partial derivative with respect to w2, we need to take w1 and yi and xi as constants. So finally, we need to the derivative becomes the partial derivative of w2xi with respect to w2, okay, which is equal to xi. Okay, so you can see that xi is multiplied by 2 and this term. Okay, this equation. Okay, note that in each iteration, also called update, the gradient is only evaluated at a single point xi instead of at the set of all samples. Okay, it is the kernel concept of the stochastic gradient descent. Okay, the key difference compared to standard or batch gradient descent is that only one piece of data from the data set is used to calculate the step, and the piece of data is picked randomly at each step. Excuse me. Okay, so next let us go to problems, if I remember correctly, problem 34. Oh, sorry, problem 35. What is gradient descent? Okay, solution in mathematics, gradient descent, also often called steepest descent, is a first-order iterative optimization algorithm for finding a local minima of a differentiable function. Okay, please note that it can find a local minima only, not always find the global minima. Okay, so the idea is to take repeated steps in the opposite direction of the gradient, or approximate gradient of the function, okay, at the current point, because this is the direction of steepest descent. Conversely, stepping in the direction of the gradient will lead to a local maxima of that function. Okay, so please note that a local maxima here. Okay, the procedure is then known as gradient ascent. Okay. Excuse me. So descent means go downward, and ascent means go upward. Okay. Gradient descent is generally attributed to Cauchy, who first suggested it in 1847. Hadamard independently proposed a similar method in 1907. Okay. Its convergence properties for nonlinear optimization problems were first studied by Haskell Curry in 1944, with the method becoming increasingly well studied and used in the following decades. Okay, next let us see the description of the gradient descent. Okay, gradient descent is based on the observation that if the multivariable function f of x is defined and differentiable in a neighborhood of a point A. Okay, please note that we are consider a multivariable function. Okay, so we do not use we use boldface A. So it is not only a point, it is also a vector. Okay, then f of x decreases fastest if one goes from A in the direction of the negative gradient of f at A. Okay, that is the negative gradient of f of A. Okay, it follows that if an plus 1 is equal to an minus gamma times gradient of f of an. Okay, for a small enough step size or learning rate gamma, which is in R plus. Okay, what is R plus? Okay, R plus is the set which contains all positive real numbers. Okay, then f of an is greater than or equal to f of an plus 1. Okay, it is easy to prove this inequality. Use the calculus. Okay, in other words, the term gamma times the gradient times f of A is subtracted from A because we want to move against the gradient toward the local minima. Okay, you can see that we use an to minus gamma times the gradient of f of an. Okay, with this observation in mind, one starts with a guess x0 for a local minimum of f. Okay, and considers the sequence x0, x1, x2, etc. such that xn plus 1 is equal to xn minus gamma n times the gradient of f of xn, where n is greater than or equal to 0. Okay, we can compare equations 43 and 44, and you can find the differences between them are that a is replaced by x. Okay, here a is replaced by x, here a is replaced by x, and the gamma is replaced by gamma n. So it is an adaptive step size or learning rate. Okay, because gamma n can be changed when n is changed. Okay, we have a monotonic sequence. Okay, or specifically a monotonically non-increasing sequence. Okay, f of x0 is greater than or equal to f of x1 and is greater than or equal to f of x2 and is greater than or equal to etc. Okay, It is 25 minutes. See you next time. Goodbye.